Okay, so I'm live with 52 weeks of AWS. I'm almost at the end of covering the AWS Solutions Architect material, and I'm going to be covering building microservices and serverless architectures today, one of my favorite topics. And maybe a few things to point out is that if you're around on Tuesdays at 5 p.m. Eastern time, one of the things that I'm doing is I'm going to begin office hours with Zoom for people that have taken courses from me, so Coursera or kind of similar courses. And I'm going to be covering questions from the audience. I also have a Discord server that I've got set up that's on my personal website. If you just go to noahgift.com and go to live streaming, you'll see links to how to get on there. But the idea here is to get, in addition to the streaming, is to get a little bit more interactive and help people out that are looking to maybe build a portfolio or become a machine learning engineer, learn more about MLOps. Also happy to talk about some of the books that I've written in that Zoom session as well, or the Discord server. So there's some new options for people that are trying to level up. All right, so that's maybe the background info, but I can go ahead and get started here. What I'm going to do is I'm going to talk about, in fact, solutions architect material around the building microservices and serverless architecture for solutions architect certification. And what I'll begin with here is just to dive a little bit into the background of building microservices. And in particular, one of the things to be aware of is what is a microservice. And really, it's a way of building an architecture that's single use. And these are independent services that communicate over a well-defined API. And so another way to think about a microservice is that they're exact opposite of what you'll hear about with web frameworks. So there was a period of time, way back into the early days of web development where there was this concept of the monolithic web framework in Python or Ruby on Rails, Django. So these concepts are basically exactly opposite of what a microservice is, because those try to solve lots of problems and potentially introduce other problems. But the new era is this microservice era, especially because of the fact that there are ways to design these things in a polyglot environment. So that's just a little bit of the concepts here. It's the evolution of web development. So in the case of monolithic versus microservice applications, you can see that in a monolithic application, they cover everything, right? You have a SQL database that maps to Python, and you go back and forth, and you do local password authentication, which in many cases is not secure, or there are security issues with it. You have all the stuff built inside, topics, messages, kind of the traditional content management based approach for web development. When you talk about microservices, though, each of these aspects of the application is individually broken out. And so you would have, for example, the user service, the topic service, the message service. They're each completely independent microservices that can be deployed actually at different times. Some of the concepts about microservices that are important to be aware of is this concept of decentralization, independence, that it's a black box. Also, that if you build it, you run it. So there's ownership there. They're specialized and they're polyglot, right? You could do C#, you could do Python, you could do Go, you could do Ruby. You could have all these different languages inside of your organization, as long as you have well-defined APIs, and these services are very simple. So in the concept of decentralization, really what we mean is that a microservice is distributed. It's a distributed system with a centralized data management component to it, and you don't rely on a unifying schema in a central database, which can really be a bottleneck in terms of deployment. And each microservice has its own view in terms of how data is architected. And they're also decentralized because they're developed, deployed, and managed and operated independently. So independence, if we get into that aspect, is that each component service in a microservice architecture can be changed, it can be upgraded, replaced. all these things can be done to it, and it doesn't affect the other service because of this well-defined API. And the services don't necessarily need to share any of their code as well, right? Because if you have code dependencies, that could slow the deployment down. In terms of specialization, this is where you would just build your microservice to solve a particular problem and move on. In terms of polyglot, the microservices don't necessarily follow a single approach as well. So if you have somebody that is a diehard .NET developer and you have a diehard Python developer, they still can work together because of the microservices. The black boxes, these are individual components that are designed as black boxes. And then if you build it, you run it. This is when DevOps is a key organizational principle for microservices. And in that particular example, the concept of DevOps is that it's really a team-based approach where you're building things in a very quick manner. So in a nutshell, microservices are decentralized, independent, specialized, polyglot. They're black boxes. You build it, you run it. These are the ways that AWS in particular thinks about microservices. So what about building microservice applications with AWS container services? In my opinion, one of the most exciting ways to do microservice development. And if I had to give someone advice about where to focus your career in 2022, I would say learning containers, learning Docker format containers, learning about AWS container services are critical to your success. So first up, we should define what a container is. And it is a microservice architecture where you can use containers for the processing power. The containers are a method of an operating system virtualization that lets you run an application. Essentially, the runtime itself runs alongside the code. And a container is very lightweight versus a virtual machine. And as a result, you have everything that's really needed to run your application. So what are the problems that containers solve? I think this is another really important concept to be aware of. One of them is that you're getting your software to run reliably in different work environments. So this could be a developer workstation. This could be a production environment. It could be a test environment. And so they allow you to actually, build once, deploy many. Another thing to consider with container terminology is this concept of basically, a Docker file. So a Docker file is a plain text file that contains all the components necessary to build a container. You can create these images from scratch, or the other thing that's kind of nice is you can build or use a container that's in a public or private container registry. So a container image is the snapshot of the file system when the container was built. So you could have a Debian operating system as a container, for example, and it would have the Debian operating system in it, or an Ubuntu operating system, which is based on Debian, or you could have a Red Hat Linux operating system. And also container images are stored in a registry, and AWS actually has a container registry called ECR. There's public registries like Docker Hub, which is probably the most popular. Now, Amazon Elastic Container Service is its own container management service. It would be a competitor to, let's say, Kubernetes. And in fact, ECS has deep integration with the AWS environment, which gives it some advantages, in fact, over Kubernetes. And so it can scale up to thousands of Docker containers in seconds. It can monitor the container deployment. It can manage the state of the cluster that runs containers. It can schedule containers by using a built-in scheduler or even third-party schedulers. You can actually communicate with it via an API, and you can also launch it with like more high-level services like AWS Fargate. So in a nutshell, ECS is a regional service that simplifies running application containers in a highly available manner across multiple availability zones within a region. A task definition is a text file in JavaScript object or notation or JSON that describes one or more containers. A service enables you to specify how many copies of your task. And ECS also lets you download your container images from a registry and run those in the cluster. So ECS offers a couple different options. You can use Fargate, which basically lets you run on top of your cluster, and you only need to package the application requirements like CPU and memory. Or if you want more control, you can actually go inside and tweak it a little bit. A few things to be aware of with the ECS service is that you can create an auto scale group, which is a good idea because you don't necessarily want to be managing scaling that up and down. It really uh, takes away some of the advantages of something like ECS, is that you want it to auto scale up and down. And this is something you can do with an ECS cluster, which is quite amazing. Now, what if I wanted to take a monolithic application, let's say some, web framework that was kind of built in the pre-cloud native era, and design it into another system? Let's say I wanted to take a Django app, which is a legacy technology, and I wanted to break it into several either fast API or Flask applications. How could you do this? Like, one way to do this would be to create an image for each of these services. The next thing you could do is choose a launch type and create a new service for each piece of the monolithic application, and then create a target group for each service. So finally, what you could do then is go ahead and build a application load balancer and configure the listener tools to connect to the services. And then the listener would check for incoming requests to the load balancer and then route those appropriately. The AWS Cloud Map and AWS App Mesh are a couple tools that are also pretty interesting. So what does Cloud Map do? It's a fully managed discovery service for cloud resources, and you can use it to define custom names for resources like databases, queues, microservices, or other cloud resources. And the other thing to be aware of is that App Mesh enables you to configure microservices to connect directly to each other via a proxy, instead of requiring code within the application or by using a load balancer. And so this is kind of a nice way, because these services can essentially discover each other and go inside and use this mesh to connect. Now, AWS Fargate, I mentioned a little bit, but it's a fully managed service. It works, though, not just with ECS. It can work with EKS as well, which is the Amazon Elastic Kubernetes service. It can provision, manage, and scale container, manages runtime, and also provides automatic scaling. So it's a way to simplify some of the complexity of using either ECS or EKS. So some of the takeaways are that ECS is really a good solution for container management on AWS. Cluster auto scaling probably is something you'd want to use if you're going to set up an ECS cluster. Cloud Map enables you to define custom names for application resources. AWS App Mesh is a service mesh for application level networking, and Fargate is a fully managed container service. Okay, let's talk a little bit more now about serverless architectures. And so one way to think about serverless is, basically, what does the name mean? And so serverless is a native architecture of the cloud. I think that's a very important thing to consider, is that, again, if we go back to some of these older application technologies like PHP or Django or Ruby on Rails, these are pre-cloud technologies, right? So they have no concept of things that the cloud is doing today. And so they're not going to have these advanced capabilities, where serverless is native to the cloud. And so it can increase your agility, innovation, and it enables you to build and run applications and services without thinking about servers. And AWS manages all the stuff that you don't want to manage, like server or cluster provisioning, operating system maintenance, or capacity provisioning. What are some of the tenets of serverless architecture? There are no infrastructure provisioning. There's automatic scaling as well. You pay for the value, right? So you only pay for the execution itself. So they can be event-driven and latent, kind of waiting to be called. And also they're highly available and secure. And so some of the benefits of serverless that are a little bit non-intuitive, and sometimes I hear people say like, oh, well, this is expensive to run serverless, but what they're people that say that are not really thinking about the TCO, or total cost of ownership, because if you use serverless, you can actually build your logic as the main problem you're solving, and you don't have to spend time maintaining services. So I've spent a lot of my life building things, And the less work I have to do in maintaining it really is what I'm looking for. So that's why I gravitate towards services. And they also fit very well with microservice applications. Now, what are some of the AWS serverless offerings to be aware of? Well, in terms of serverless here, there are a lot of different options, including Lambda is a good example of serverless. Step Functions is a good example of serverless. Athena, right, a big data system is a good example of serverless. Okay, let's get into Lambda, which is one of the predominant ways to do serverless. Probably one of my favorite services on AWS. It's a fully managed compute service. It allows you to run your code on a schedule or in response to events. So I use this a lot if I want to maybe do some kind of change to a file that's uploaded to S3. That's a great example. Or I want to respond to a message in SQS. That's a good example. Lambda supports Java, Go, PowerShell, Node, C#, Python, Ruby, and you can run it at edge locations close to the users as well. So Lambda is probably the first stop when you're thinking about serverless on the AWS platform. So how does it actually work? And this is a really important distinction to be aware of, is that it really works with the whole architecture of AWS, and it's custom code that you write in one or more languages, and you can configure a trigger. So really the trigger is what invokes the function. And this is in response to some type of life cycle event. Like again, I put a file inside of S3, it sets up an event, and then that is the trigger that I'm actually listening for. But it can be lots of different kinds of events inside of AWS. An event source is the entity that publishes that event to Lambda, and the Lambda function processes the event, and Lambda executes the Lambda function on your behalf. So Lambdas are actually stateless, which means they really don't have any affinity to the underlying infrastructure. They don't care about it. And Lambdas can launch as many copies of the function as needed to scale to the event. So really that's a huge advantage in the architecture itself, as long as you're able to build your system according to that architecture. So what are some things to be aware of that you need to know about? Well, I think a few things to be aware of is that you need to have the correct access permissions. So if you wanted to communicate with the S3, right, you need to have access to it in an IAM role. You need to have the right trigger event set up. So if you're going to talk to S3, for example, you need to connect that trigger. You'd also need the application code and the dependencies as well. And then any kind of configuration like how much memory or CPU, et cetera, you would need. So those are really the core components of what's necessary to write a Lambda function. Now, what are the pieces of a Lambda function? Fortunately, pretty straightforward. There's a handler. This is really the function that's going to be executed upon invocation. And the code execution begins at that handler. And the handler always takes two different objects. The first object is an event object. The event object is basically a payload that comes in as a JSON stream. And the contents of the event object is all the data and metadata the Lambda needs to basically drive the logic of the function. The content and structure of each event is going to be different depending on which event source created it. So if it's from S3, that could be one event source. If it's from, a authentication system like Cognito, that's going to be a different source. The context object is generated by AWS, and it provides metadata about the execution. And that's the big thing to be aware of here. So at minimum, the context object contains an AWS request ID, a log stream name, and also get remaining time in millis. These are all things that are available to you if you want to interact with them programmatically. So what about the configuration and billing? The memory is the cost per 100 milliseconds of function duration. The timeout is you control the maximum duration of the function. And then the pricing is what you're charged according to the requests. So what are some of the best practices here would be to test the performance of the Lambda function to make sure you're choosing the right memory config. Also load test your Lambda function to analyze how long the function will actually run so you have the best timeout value. So if you're not doing some kind of load testing in general for software architecture, you're going to eventually get yourself into a problem where the non-deterministic aspects of your code can get you into trouble. And so that's where you really do want to configure the timeout value based on your load test. Okay, so let's talk about using a Lambda function to, let's say, have a simulated slot machine browser game. How would you do this? Well, you could create a Lambda function that does a few different things. Maybe it goes in and invokes something that pulls in a payload, and then afterwards you would return back the slot, basically a random value, right? It's either a cherry, a puppy, or a robot, right? And that's a really good way to think about how you could build one. You could do an event-based Lambda function for order processing. So for example, you could have a customer upload a transaction file to S3 bucket. Then that creates an event, which then triggers a Lambda function. The Lambda function would then process that transaction file and update the customer and transaction DynamoDB tables. You could also go through and change the transactions DynamoDB table trigger to have a second Lambda function aggregate the transactions and update the totals in the transaction total DynamoDB table. And then you could push that message to an SNS topic. Finally, the SNS topic will then send maybe an email notification to a customer and update the credit collection and customer notify SQS for payment processing. So Lambda layers here, these are some things to consider. They're actually really useful because what they do is they enable you to share code easily. So you upload a layer and then you reference it inside of any function. And so let's say you're using a common, set of tools for most of your applications. Let's say it's Python, you're using Boto 3, maybe scikit-learn, pandas. You could put that inside of there. And then your deployment package is actually a lot smaller. You can have up to 5 layers at 250 megabytes each. Okay, so let's talk a little bit more here about some of the things you can do. Like, for example, if you are building serverless architectures, most likely you're going to want some kind of web interface for it. And this is where Amazon API Gateway comes into play. It's a fully managed service that enables you to create, publish, maintain, monitor, and secure APIs at any scale. And you can use it to create a REST-based or WebSocket API that is an enter point for your application. So both of those are really tricky to do at scale, but this enables you to create, publish, maintain, and monitor that secure API. It also lets you handle up to hundreds of thousands of concurrent API calls. So this is awesome that I can just give this to AWS and say, hey, handle that for me. It works with Amazon EC2. It works with Lambda. It works with any web application. Also, because of the WebSockets interface here, you can do real-time communication applications. You can also host and use multiple versions and stages of your API. So what about the security for Amazon API Gateway? Well, first up, you would need to require authorization. You need to apply the resource policies. You also need to have some kind of throttling, right? This is really common because people will abuse your API. What is the throttling policy that you want to have, or your settings? And then how do you protect it from a distributed denial of service attack or injection attacks? These are all things you get with AWS WAF, or Web Application Firewall. So why would you want to use this? Well, the API Gateway is a API layer for the application, and it's a common way of using an architecture on AWS. So for example, you could have a front-end client and application server send traffic to API Gateway over the internet. And then CloudFront is used to cache the static content, because CloudFront, as we know, can distribute content to edge locations all over the world and give very low latency requests back a fast response. And API Gateway will abstract and expose APIs that could do various backend applications. Again, these talk to Lambda, Docker, EC2, VPCs, and finally, these are monitored with AWS CloudWatch. And you can use API Gateway with other managed services to build really sophisticated serverless backends for applications. API Gateway is also deeply integrated with AWS Lambda. And so you could potentially set up a microservice that takes HTTP API calls and hosts a RESTful request and response to the customers. And API Gateway provides built-in authorization, throttling, security, fault tolerance, and request response mapping and performance optimizations. AWS Lambda contains the business logic to process incoming API calls as well, and it uses DynamoDB as a persistent storage service. Some examples would be the serverless mobile backend. And a good example of this would be a mobile device really could use something like API Gateway or a mobile application because it allows you to build a fully serverless backend for, let's say, an iOS or Android device. What about orchestrating microservices with step functions? Yet another one of my favorite services on AWS is step functions because they allow you to kind of build a guided pathway. And one of the problems is if you build too many microservices, there's no way to necessarily cleanly orchestrate them. And if you get timeouts, they can cause cascading problems. But if you use step functions, you can really coordinate a workflow and get really good debugging. And so these are visual as well. They enable you to step through the functions of your applications. I've actually got a pretty good demo up on the O'Reilly platform you can take a look at of how to get started with step functions and Lambdas. And also you can automatically trigger and track each step. And you can finally provide a simple error catching and logging if the step functions fail. So that's really the monitoring and instrumentation is pretty powerful. And so some of the things you can do would be run tasks in a sequence. You can select a task based on data. You can manage try, catch, finally behavior. You can run tasks in parallel. You can retry failed tasks. Really, it's a state machine, really. And that's the main thing to be aware of. It's a collection of states that can do work. And a common example of a state machine is a vending machine. And the vending machine is where the machine starts in an operating state. So it's waiting for a transaction. And then when you go through and you put the money in, that moves the soda selection. And then it finally enters the vending state and the soda is deployed to the customer and then returns back to the waiting phase, right? So this is really a good example of how step functions work. And so states are really the concept of where it is at in a particular part of a workflow automation. And some of the things you can do inside of step functions include a task, which is a single unit of work, a choice, which is branching logic to a state machine, fail, which stops an execution and marks it as failure, succeed, which stops an execution, passes its input to its output, wait, delays from continuing for a specified time, parallel, creates parallel branches, map, dynamically iterates steps. And so the other thing that's really awesome about step functions is that they're basically a JSON-based structure as well. And you can check that into some repo. A good thing that you could think of as a use case for a step function would be a video on demand architecture where you're basically processing data as it comes into S3, doing all kinds of transcoding and then putting it to some other location. So in a nutshell, really the step functions are quite amazing in terms of what they can do. And I would definitely recommend using step functions. Again, check out some of the stuff I have on the O'Reilly platform around step functions and also AWS Lambda. All right, so that's it for today. Quite a bit of material that I covered. What I'm going to cover next week is how to prepare for disaster. And unfortunately, I have a lot of experience with this. I've actually been burned many times in putting things into production. And I've had problems where the backups didn't work. And then I went to retrieve the backups and the backup was the same backup file. So I have a lot of experience with failing in terms of production, deleting customer data. And so I'm really excited to talk about that next week. All right, we'll see you next week.